2.1 task. We are going to quickly review the distance between area and perimeter. If you had a square or a rectangle, let's do a square with side lengths of 2. The perimeter would be 2 plus 2 plus 2 plus 2, or the perimeter would be 8 units. That's the area around. If instead you wanted the length around. If instead you wanted the area is length times width, or 2 times 2, which would be 2 squared, or in this case 4, because if you really looked at it, it would have 4 blocks in the inside, so it's 4 units squared. If instead of having an actual length for the sides, we called this side x and this length x, then the area would be x squared, and that is what we're going to talk about today. Optima Prime is designing a robot quilt for her new grandson. She plans for the robot to have a square face. The amount of fabric she needs for that face will depend on the area of the face, so Optima decides to model the area of the robot's face mathematically. She knows that the area of a square with side length x units, which can be in inches or centimeters, is modeled by the function a of x equals x squared unit. What is the domain of the function in this context? Think, what are the possible lengths, of the square? Well, it can't be less than 0, and it actually can't be 0, because if the lengths were 0, then you wouldn't have a square, and theoretically it could be really, really long. Now, it can't go to infinity, but we don't know what the maximum length is, so we're going to say the area can be decided by the side lengths, which would have a length from 0 to infinity. X, the length, has to be greater than 0. Again, remember, x is what you put in the function, so you put the length in, and then it tells you how big the square is. Now it says, predict on the graphs of each of the following equations the differences from the graph of y equals x squared. So you guys will be using your calculator for this task, and what you can do is go to y equals and type these in. The original equation is x squared. This is the original equation that Optima has, and here it is. So if we have a length of 1, we have an area of 1. If we have a length of 2, we have an area of 4, because 2 squared is 4. If we had a length of 3, we'd have an area of 9. And you can see that in the table right here. If we had a side of 1, the area is 1. Side of 2, area is 4. Side of 3, area is 9. But what happens if you put 5x squared in front of it? Or 5 in front of the x squared? So I'm going to put the 5 right here. And you can do this too, put 5x squared and then hit graph. And you can see that it got skinnier. Okay. What if you put the 5 inside? So basically we're doing 5 times the whole area. So the area got skinnier, okay, which means it's going to get bigger faster. What if you made the length 5 times longer? Well, instead I'm going to take this out and do parenthesis x plus 5 squared. There's the original. Oops, I must have done something wrong. Let's see. Oh, there's too many parentheses. Go back and delete one set. There we go. There's the original. And now you can see that it moved over 1, 2, 3, 4, 5 to the left, which is kind of weird because I would think that a plus would go over here because it's positive, negative, oops, positive, negative, negative, but it actually went 5 that way. Now I wonder what if we put a 5 on the inside would do. So that's basically making each length 5 times longer. There's my original. It made it super skinny, so it got even skinnier, or it did a vertical stretch. Okay. And then lastly, what do you think the plus 5 would do? So now we're taking the whole thing and adding 5 to the y. So here's the thing, and then we add 5 to the y, and it went up 5. So this is kind of what we're going to be looking at. What moves it left, right, up, and down and makes it skinny or fat, and you'll use your calculator to help you. So it says, Optima started thinking about how the graph of y equals x squared in the domain of all real numbers, and wondering about how changes to the equation of the function, like adding or multiplying by 5, would affect the graph. She decided to make predictions about the graph and check them out. So again, let the length be x, and we're going to match this to an algebra tile representation, not just a graph representation. So it said the length of each side of x is increased by 5 units. So basically, okay, you have your little square here, x, and then we're making it 5 inches or 5 whatever longer on this side, and 5 longer on this side. Okay, the x is the domain, so that would actually be this one right here, x plus 5, and then you turn it into a square. So x plus 5 turned into a square. And if we were to simplify this, we would have x plus 5 times x plus 5, and FOIL it, that would be x squared plus 5x plus 5x plus 25, which would give you x squared plus 10x plus 25. That's just another way to write it. And if you look at that, that's what we have right here. This is an x times an x, so this is an x turned into a square. This is a length of 1 times the length of x. 1 times x is x, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 x's. And a length of 1 times a length of 1 is 1. There are 25 ones. So that's a picture of that one. The next one says the length of each side is multiplied by 5. Okay, so that would actually be either this one or this one. And if you think about it, we want the side multiplied by 5. So it's just going to be the x of the inside. So it's going to be this one. We have a length of x, but it's 5 times longer. So 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. And then it's turned into a squared. So see 5 times x turn into a square. So it's this one. And if we simplified that, this is the same thing as 5x times 5x, or 25x squared, which is what we have here. We have x squareds, and there are 25 of them. So again, this is C, and this is B. Let's look at the last two. This is just to introduce you to the different types of representations. All right, so the next one, the area of a square is increased by 5 units. Well, here's the area of a square, and then we've just added 1, 2, 3, 4, 5. So that's this one, the area of a square, and we've added 5. And that one, there's no simplification needed. It's just the same. Okay, this is the one that went up 5. And so lastly then, this must be the pink one. Oops, I needed to move this up here. Okay, and it says the area of the square is multiplied by 5. So here's an area of a square, and there are 5 of them, times 5. And that also doesn't simplify, it's just 5 of these x squareds. So that's one way to look at them. Here we looked at them on a graph. Here we're looking at them in kind of algebra tiles. And now let's put this all together. Optima decided to test her ideas using technology. She thinks that it's always a good idea to start simple, so she decides to go with x squared plus 5, which is what we did right here. Goodness, where did it go? There we go. Notice it just went up 5. Okay, and so if you were to type this in again, you would see that it went up 5. Okay. Knowing these things makes a lot more sense with more representations. Optima tries a few more examples like x squared plus 2 and x squared minus 3. Looking at both the table and a graph for each, what conclusion would you draw about the effect of adding or subtracting a number to x squared? So I'm going to show you a couple of these, and then I'm going to have you do the rest. Okay, so this is the original function y equals x squared, and you can get those values from hitting second graph table like I showed you. Or if you put negative 2 into the equation, negative 2 squared is 4. So at negative 2, we're up 4. Okay, at negative 1 squared, minus 1, we're up 1, etc. This is the parent function. This is where we always start. And then we want to see what happens when we subtract 3. So you're taking x squared, which would be this value here. When x is negative 2, x squared is 4. Negative 2 times negative 2 is 4. And then you're minusing 3. So you're really saying, take all of these x squareds, take this side, and minus 3. So 4 minus 3 is 1. 1 minus 3 is negative 2. And if you graphed those, you would get a new graph that shifted down 3. And so what you will do is do that on your calculator and write this in before you turn it in. Graph. So you can actually get it from right there. There's the original. There's the new one. And if you hit second table, you can actually see it's 0, negative 3. So at 0, it's negative 3. If you want to push up, there it is. Okay. Negative 2 is 1. Negative 1 is negative 2. Here's your values, and here is your new picture. What happened? It went down 3. Okay. I'm going to let you do this last graph. And then you should be able to fill in some type of simplification, such as if you add k to it, it'll go up k. And if you subtract k to it, it'll go down k. And what I mean by k is we subtracted 3, so it went down 3. You are going to do the same thing with adding on the inside and subtracting on the inside. And you should get a new graph. And you can freeze this and write down the answers. Okay, so this one you can see that if you add k, it goes to the left. And if you subtract k, it goes to the right. What you have to do is get the correct graph. And then you're also going to see what happens if you put a negative in the front. And I'll leave that one up for you. You tell me what happens right here after you draw the graph. And if you put a number in the front, and I will give you this one as well, you can freeze it and write it in, but you need to put it in your calculator. I'll do this one to see what happens. So you'll do the rest with your calculator, fill it all in, and turn it in for credit if you were absent.